Okay, thank you very much. First of all, I'd like to thank the organizer for inviting me this very nice workshop. Today, I'd like to discuss some phase transition on some vortex in the strong coupling regime to the weak coupling regime. And this is a work in collaboration with Dan Kondo, University of Tokyo, and Tomoya Hayata in Keio University. And this is working based on this recent paper. Okay, let me start with my summary of this talk. So in this talk, we want to focus on some gauge theory with U1 global symmetry. And so for example, if you don't have the matter field in the gauge theory, for example, SU and gauge theory or U1 gauge theory in the lattice formulation in 3+1 dimension. So if you go to the strong coupling region, you will have some confined phase. And if you go to the weak coupling region, suppose, for example, the U1 gauge theory, we have the Coulomb phase that we call here the deconfined phase, or any parameter is okay. But anyway, so usually we gauge theory has several phases. So in the modern language, this corresponds to the unbroken phase of the higher form symmetry, and this is the broken phase. So now if you turn on the matter field, for example, adding the charged matter with the fundamental charged matter and Higgs in it, then usually this phase is phase transition disappear because of the fundamental matter breaks the higher form symmetry explicitly. And here, we want to ask some another possibility. If you turn on the broken U1 gauge symmetry, in some, then this phase will be the, and also the consider the this phase, global symmetry is spontaneously broken. Then we will have the superfluid phase here. And the superfluid phase, we have the some emergent symmetry that is a two-form U1 symmetry that corresponds to the existence of the superfluid vortex. Then even if there is no phase transition on this one, if you put the superfluid vortex, then something happens between this region and this region. So in this talk, we identify that this is kind of the confined regime, and the weak coupling we call the Higgs regime. But anyway, so on the if we put the vortex here, so we will have some phase transition on this vortex. So of course, it depends on the theory. So I will show you some example. This will happen. So before discussing this talk, so I want to show you some motivation and the current status of our community on the confinement and the superconducting phase phenomenon. Okay. Okay, let me start with the motivation. So I want to understand the phase diagram of QCD. So this axis is a temperature and this is a chemical potential. QCD is a SU3 gauge theory with fundamental quark. And if you go to the very high temperature or high density region, so we'll have the quark-gluon plasma. And if you go focus on the low temperature region, so at the high density region, we'll have the superconductor phase. So what we know is that this region and the very high density region and this region, where we can use the nuclear physics technique. So unfortunately, we cannot simulate on this region because of the so-called sign problem in the lattice gauge theory. So, but we want to understand this region. So what we know, so the other simple example, we consider the 3-flavor QCD, which have the SU3 flavor global symmetry and U1 baryon symmetry, in addition to the gauge symmetry. So in the low density region, we will have the superfluid phase of the condensation of the baryon. So this is the QCD. So the fundamental degree of freedom in the vacuum is so-called the baryon, like a neutron and protons and so on. So in the SU3 case, the so-called lambda baryon will be condensed. Then the global symmetry breaking pattern is SU3 flavor times U1 baryon go to the SU3 flavor. So this is a low density region. So if you go to the very high density region, the scalar superconductor will be realized due to the quark pair condensation. So this is just a example. But the important point is that global symmetry breaking pattern is actually the same. So since this is a condensation of the baryon or quarks, then this two phase the all color superfluid phase because of the breaking of the U1 baryon symmetry. So this is a basic system. So now this region is U1 breaking, and this region is also U1 breaking. So the people conjecture that this region is smoothly connected to this region. That is called the quark-hadron continuity. Okay. So now, we can ask the question: so can these two phases are distinguished for some topological reason? So now we know the existence of the global symmetry, generalized global symmetry, and also there are many possibilities of the SPT phase or topological ordered phase and so on. So roughly speaking, the topological ordered phase is a spontaneous broken of the generalized global symmetries. Okay, in some sense. So now we want to ask these kind of possibility. So I don't need to explain the detail, but let me briefly remind you what the generalized global symmetry is. The ordinary global symmetry is in D plus one dimension, QFT, is a pair of the codimension one symmetric defect and charged object. So this operator is actually topological, and the multiplication of the operator satisfies the group law. And charged operator is some kind of the labeled by the representation of this group. And if you this symmetry defect pass to the point operator, you will get some representation matrix. This is just a transformation law of the ordinary quantum field theory. And or equivalently, if you surround the charged particle by this symmetry defect and shrink it, then you will get this kind of transformation. So this is a transformation rule of the ordinary symmetry in the QFT. So you can generalize this notion to the two direction. One is a non-invertive direction. That is now the group law can be relaxed to the law of the algebra. Or you can generalize this notion to the higher dimensions. That is called the higher form symmetry. And now the higher form symmetry is a pair of the object that is a codimension p plus 1 object, topological object, and p-dimensional object labeled by the group representation. And this is labeled by the group. That is the higher form symmetry. And also satisfy the group law. And now if two operators are linked each other, then we'll get the representation matrix here. So this is a general higher form symmetry. So now the simple example is the U1 gauge theory. The charged object is a Wilson loop or a 't-Hooft loop given by this operator. And the symmetric operator, symmetric charge is nothing but the electric flux and magnetic flux. The higher form symmetry is just nothing but the flux conservation of the electric and magnetic ones. Okay. So the modern language, if you consider the QED, so now that we have the fundamental matter of electric charge, meaning that the electric one-form symmetry disappears. But if you go to the vacuum or superconducting phase, there is some emergent symmetry anyway. But we still have the U1 magnetic symmetry. So vacuum corresponds to the spontaneous broken phase of this U1 magnetic symmetry, and the superconducting phase corresponds to the unbroken U1 magnetic symmetry. So when spontaneous symmetry breaking happens, often appears the emergent symmetry. So in this vacuum case, we will have the emergent electric one-form symmetry that corresponds to the electron is heavier than the scale that we are interested in. So in this case, this symmetry is spontaneously broken. The photon can be understood as the Nahm-Grosson boson associated with this symmetry breaking. And also the superconductor has some emergent symmetry, which is Z2 one form and Z2 two form symmetry, whose symmetry is spontaneously broken in some sense. Then this theory exhibits the topological order. So this symmetry breaking meaning that the Cooper pair has a charge 2. And also that this the two form symmetry, meaning that this is a superconductor, so we have the vortex, local vortex. The inside of the vortex can have the pi flux instead of the 2 pi. So this is the origin of the emergent symmetry. So yeah. So now I want to ask the thought experiment. So let's consider the QCD in the this is the let's consider the neutron stars. That is a very dense quark matter. And the core of the neutron star will be the color superconductor. This is an assumption. And outside of the region will be the hadronic superfluid. Then if you're rotating the neutron stars, we will have the superfluid vortex inside of this one. Then another question is that this vortex, are these vortex smoothly connected or not? By using the global symmetry. Okay. So in particular, we will focus on the two quantity. The one is the circulation and also the discuss the emergent symmetry.
Sir, can I ask a question? Like, what do you mean that there is a vortex inside? It's like a vortex loop, or it's like a bunch of vortices, or?
I will discuss just one single vortex, but in general, if you're rotating the system, then we will have the bunch of the vortices inside.
But how can you have like a single vortex in a three-dimensional system that is like, I guess, a neutron star?
It is a rotating system, so we have the angular momentum.
Yeah, but what are these vortices? Like some loops, or they like extend from the core?
Vortex appear along to the rotational axis. Okay. So now let's come back to the detail of the system. So now in the low density region, as I said, this is a dicroc is a condense, and symmetry breaking pattern is this one. So since this is a broken U1 phase, we'll have that superfluid vortex. So here is the order parameter operator, and suppose that this kind of configuration, theta is the azimuthal angle, and with some boundary condition, we'll get that vortex solution in this case. This is a so-called U1 vortex. And the U1 vortex in the hadronic phase has a circulation, so which is rotation of the velocity times some circular integral of the velocity of the field. So which is the ratio of the momentum density by the energy density, which is proportional, is equal to this one, and gives you this circulation number. So here nu b is a winding number, and to mu b is nothing but the baryon chemical potential of the order parameter. So now this is a dibaryon is condensed, which has a baryon number 2. So this is 2 mu b corresponds to such fact. So this is the circulation in the hadronic phase. So if you see the dense quark matter, in particular the color flavor locking phase, so if you turn off the interaction of the QCD, so we'll have this kind of Fermi. The mu q is the quark chemical potential. Then we can consider this kind of condensation. The detail is not so important. The main point is that this condensation has a 3 color index and flavor index. So this looks like the 3 by 3 matrix. And CFL phases correspond to this configuration. It's a diagonal. So meaning that then we can consider the U1 vortex in this configuration. So that is a rotation around this diagonal phase. Okay. So, and also it is known that there exists another vortex, so-called the non-abelian CFL vortex. That whose configuration something like this. In this case, U1 phase is appearing in the all diagonal component. In this case, this just only one component is rotating. This configuration can be decomposed into the global U1 part and SU3 part like this. And also in this case, the gauge field has some non-trivial configuration. So which means that this U1 vortex has a property of the superfluidity, that is this phase, and also the property of the superconductivity that corresponds to the this region. Meaning that inside of this vortex there is some magnetic flux. So in the numerical simulation, it is known that this U1 vortex is unstable, and which decay into the three non-abelian vortices. So the stable one is actually this vortex. So now let's consider the quantum number in the hadronic phase and color flavor locking phase. So we have the several vortices. In the U1 vortex in the hadronic phase has this circulation. And the U1 vortex in the color flavor locking phase has this kind of circulation. This is a similar formula. So 2 pi times winding number divided by the chemical potential of the order parameter. In this case, this is a dichrome condensation, meaning that this is 2 mu q. Can be written in this form. So there is some relation. The baryon chemical potential is 3 times larger than co-chemical potential by definition. So we'll have this kind of circulation. And also that you can calculate the similar things for the non-abelian vortex. So now, since this phase is you have the third here. So which means the winding number is not the integer, but the 2 pi divided by 3. So this fact corresponds to the circulation is divided by 3. Then now the total circulation becomes this one. So if you match the circulation, you will expect that this vortex should be the smoothly connected to this one, not this one. However, if you focus on the magnetic flux inside the vortex, which is measured by the Wilson loop around the vortex, that's measured the holonomy. So we will have the additional factor here. So which means that this vortex does not match with this vortex from the point of view that this flux. So in this observation, so the Alexei and Sen and Yaffe propose there is some this phase will be the topological phase. But however, unfortunately, this is not the topological order phase because since there is a magnetic flux inside the vortex implies the emergent Z3 two-point symmetry. So this will be true. However, this symmetry is not spontaneously broken, unlike the ordinary topological order. Because this is a superfluid, this system has a superfluidity, so which means the interaction between the vortices has some logarithmic potential that breaks meaning that's unbroken of the two-form symmetry. So this is a not topological ordered phase. Topological ordered phase, this emergent symmetry should be the spontaneously broken. Then the question is what is the fate of this Aharonov-Wien phase? So the one possibility is there is some phase transition, between the hadronic phase and dense quark matter phase. But there are another possibility. So if even in the hadronic phase, if you calculate that is a strongly coupled system. So usually it's very hard to calculate the system. But in this region, sometimes this phase can appear in the hadronic phase. So which means in the hadronic vortex has some non-trivial magnetic flux. Or another possibility is since this is an emergent symmetry, so between the hadronic phase to the quark phase, so this phase is gradually disappears. So this possibility that was shown. So now, yeah, still what happened, we don't know. But today, in this talk, I want to discuss a different point of view. So since we are interested in the vortex, so the question is can we discuss the question is there any phase transition on the vortex or topological defect between the strong coupling region or weak up to the weak coupling region? So for example, if we consider domain wall or vortex, so in this talk, we want to focus on the vortex. So since this effective theory on this topological defect is a kind of the field theory in the lower dimension. So for example, if we consider vortex, the effective theory is a 1 + 1 dimensional field theory. So if you change the parameter of the bulk, then there appear some phase transition on this vortex. So this will happen in the situation of the some gauge theory. Okay. So our model is very simple. So we will consider the abelian Higgs model with two Higgs. So to explain the phase diagram, so let me start with phase diagram with just a single Higgs field. That is called the Shradkin-Shenka model. So the action of the model has this form. So here, F mu nu is the field strength on the lattice version of the field strength. And this term corresponds to the compact U1 scalar field coupled with the gauge field with charge Q. Here, delta is just a lattice difference. So it is known that this phase diagram. So in the case of the charge is equal to 1, so there is two phases. So one is a Coulomb phase. So that appear in the small h. That corresponds to the strong coupling region of the this U1 system. So if there is no gauge field, that theory becomes a gapped system. Then if you turn on the gauge field with weakly coupled case, that corresponds to this region. So we will have the Coulomb phase. So that corresponds to the emergent U1 electric and magnetic symmetry system. And on the other hand, if you go to the strong coupling region, so we'll have the confined phase usually. Then if you change the coupling constant to the weak coupling region, so we'll have the smoothly connected. So this is kind of the confinement Higgs crossover here. Then, because this is the case where the charge is equal to 1. If charge is not equal to 1, so we'll have the three phases. That is the confined phase and Coulomb phase and Higgs phase. So this Higgs phase is nothing but the spontaneous broken of the one-form symmetry. So if the charge is 2, then this system has a Z2 one-form symmetry. So we can distinguish these phases like this. So now let me explain our model. So this is a U1 gauge theory with U1 global symmetry. So this is just a two Higgs system coupled with the U1 gauge field. So how much time do you have? Finish? Oh, I think that it is really enough for me. Almost done. So this is a system. So this system has a global symmetry and gauge symmetry. So since this operator coupled to the U1 gauge field, so we have the U1 gauge symmetry. In addition to this symmetry, so we'll have the U1 global symmetry with some U1 phase rotation is the opposite. And we have some discrete symmetry for the here we call the flavor symmetry. That exchange the phi 1 and phi 2. Okay. So now let's discuss the phase diagram. If there is no just if this is a single Higgs field, then we'll have this kind of structure. So now turn on the if we consider the two Higgs system, then if we go to the weak coupling region of the scalar field, so we'll have the superfluid phase. Then we change the coupling constant from strong to weak. So what we found is actually that in the numerical simulation, so there is no phase transition between this one. But if you put the vortex here inside the system, then we'll have some phase transition. So to show, okay, in addition to the this global symmetry, and in the large coupling region, we'll have some emergent symmetry corresponding to the U1 two-form symmetry and the two-form symmetry. These are corresponding to the existence of the superfluid vortex, and this explains the existence of the magnetic flux inside of vortex. So which means if you have the vortex here, so this vortex has a magnetic flux inside the vortex, and also that if you go to the strong coupling region, this vortex still have the non-trivial flux inside the vortex. Yeah. Okay, let me analyze the two limits. One is a strong coupling limit, corresponding to the gauge coupling, inverse of the gauge coupling is small, or weak coupling region. In the strong coupling limit, so we can integrating over the degrees of freedom of the gauge field. Then we'll have this kind of action. And if you go to the weak coupling region, we'll have this kind of action. So here, I0 is just a modified Bettinger function. The important point is that in the strong coupling region, the degrees of freedom is a phi 1 minus phi 2. On the other hand, we have in the weak coupling region, we have the independent phi field here. So roughly speaking, in the strong coupling region, the degrees of freedom is just a single phi. The combination is a phi 1 minus phi 2. On the other hand, in this region, we'll have the phi 1 and phi 2, so which implies the spontaneous breaking of these symmetry. So this is not obvious. So let me to capture this phenomena, let's consider some symmetry defect or twisted boundary condition. So now we put the U1 vortex in the system, then we consider some boundary condition of the vortex that is twisted boundary condition by the D2 flavor symmetry. Then we can ask that there exists a domain wall inside of the vortex or not. So if this D2 symmetry is spontaneously broken, there appears some domain wall. On the other hand, if the D2 symmetry is not broken, then there is no domain wall. So simple example is very known in the Ising model. So in the Z2 broken phase, if you put the antiperiodic boundary condition, then we'll have some domain wall inside of this one. Then this domain wall has some finite energy. On the other hand, in the high temperature region or large transverse magnetic field region, so we'll have the randomized spin. Then if we impose the antiperiodic boundary condition, that there is no domain wall here. So similar things happen in this our model. So in the weak coupling region, so we'll have the some vortex of this phi 1 field. And because of twisted boundary condition, so we have this region should be the phi 2 field. Then there appear the single vortex domain wall. And on the other hand, the string coupling region, we found that there is no such a structure realized. Yes.
This Z2 flavor is a symmetry of the whole theory.
Whole theory, yes.
But then why is it? I mean, why don't you have like a local order parameter? And why do you have to look on the vortex and not?
Yeah, actually, yeah, this is somewhat the vortex is some kind of the extended object. So there is some local like order parameter. Yes. That is the value of the electric, magnetic flux. Or
okay, I thought that this Z2 is a zero form symmetry.
Yeah, in this case, so the vortex is a one-dimensional object, but the zero form symmetry can act the extended object. This is not higher form symmetry. Yeah, looks like that. Yeah.
No, my question is, why don't you look for like a local order parameter?
Yeah,
in 4D. I mean.
Yeah, that is local order parameter on the vortex.
No. I mean, well, okay.
If there is no vortex, there is no phase transition.
Okay.
Phase transition only happens on the vortex.
I guess my question is, this Z2 to be defined needs a vortex?
Vortex. Yeah.
Or the Z2 you can define it in all the system.
Whole system.
Then the notion of Z2 being broken or not is independent of the presence of a vortex.
Vortex. This Z2 trivial act on the vacuum, but not trivial act on the vortex.
Okay.
Well, yeah. Of course, you can consider the order parameter, but this is the alternative approach.
Okay.
Yes.
Okay.
Yes. Thank you very much. On the lattice, if you calculate the 1-point function of the order parameter, it will vanishes because of the summation of the. Yeah, of course, that if you consider a 2-point function of the order parameter, then the long distance, it will finite. So actually, we did such a thing in the numerical calculation. So here, I want to show you the numerical calculation. So in this case, we calculate the correlation function of the magnetic field inside of the vortex. That is a correlation function. So this is a correlation function as a function of the distance. So you can see that along this that this different line corresponds to a different coupling constant. So if the coupling strong coupling region corresponds to the this region, you can see that at long range distance, so the 2-point function decay goes to the 0. Then on the other hand, if you go to the weak coupling region, we will have the finite 2-point function. That is the signal of the spontaneous breaking on the vortex. So we also check the critical phenomena and the universality class. So here is a susceptibility as a function of the coupling constant, and with a different volume. So this is just a raw data, and if you scale by using the critical exponent, nu and gamma. So that this line becomes something like this. So if you go to the large volume limits, that coincide with each other. Then we find some critical value, and also the this result is consistent with the universality class is actually the Ising model, like this. So let me summarize my talk. So what we found is that the phase transition on the vortex, even in the bulk, is smoothly connected. So there is some possibility of the phase transition on the topological defect. So this is just a simple example. So more generally, maybe we can consider some various type of the phase transition on the topological defect. So for example, if we consider the codimension 1 defect, that corresponds to the domain wall. So the codimension 2 is this is our example. So if we consider the codimension 3 in 3 plus 1 dimension, then that is not phase transition because that is a point 0 plus 1 dimensional QFT. That is nothing but quantum mechanics. So we don't have the phase transition, but we observe the level crossing phenomena. Or more generally, we can consider some phase transition on the junction of the, for example, the domain wall and so on. So in this talk, we discussed the U1 cross U1 model. But in what we really want to do is a QCD. So unfortunately, in the case low energy effective theory of the QCD, the vortex effective theory is a CP2 model. So which means there is no such a interesting phase transition, unfortunately. But however, in the QCD has some non-trivial fermion. So it is known that the inside of the vortex there exists some Majorana zero mode. Then the question is what happens if you couple the CP2 model with some Majorana fermion? Might be something happen. But that is the future work. Okay, thank you very much.
I didn't really understand the point about the codimension 3 defect and level crossing. Could you re-explain that, please? I didn't understand the point you made about codimension 3.
Codimension 3?
And level crossing. Could you explain that again, please?
Okay. Codimension 3 means that the defect is a point defect. And that's space-time.
This would be a point in space?
Yeah.
Okay.
Not point. In the space-time, that is one-dimensional, like a Wilson line. Yeah. But this is just a 0 plus 1 dimensional QFT. This is just quantum mechanics. So something happen, but that is not phase transition.
So
yeah.
So would you say this is a first order transition if this is level crossing?
Level crossing case, yeah, looks like the first order. For example, if you put the Wilson line in the system, then, for example, if you consider the confined phase, then because of confined phase, the antiparticle coming to the Wilson line to neutralize the Wilson line.
Okay, so just so I make sure I understand. So by level crossing, you just mean there'll be some first order transition.
First order, yeah.
Okay, that's all. Okay, thank you.
Okay, yeah.
Thank you. That was super interesting. I'm wondering, have you thought about what would happen if instead of considering your model in 3 plus 1 dimensions, you worked with it in 2 plus 1 dimensions?
Yeah, we haven't studied the 2 plus 1. This is 3 plus 1 dimension.
Okay.
Yeah.
I understand. Yeah, the reason I'm asking is that in 2 plus 1 dimensions, the vortices are 1D objects.
Right.
And then it's much harder to see how you could have a phase transition on the vortex.
Right.
Because
yeah. This is a case for the level crossing, actually.
Yeah, but the interesting thing about level crossing is you don't get it for free. The only way that it could really be robust is if you have some Swift anomaly or something, right? I mean, and there's no obvious source for that. Normally, level crossing is resolved, right? So the systems where it's really there are super special.
Yeah.
Okay, but yeah, fair enough.